We're talking about time series data and the seemingly invisible statistical mirage that occurs when data behaves badly. Our goal today? To unmask that mirage and find the truth.
Okay, let's dive into this. Here is our step-by-step agenda for today. 1. The spurious regression problem. 2. Defining stationarity. 3. Trends and unit roots. 4. Testing the data. And 5. How to stationarize data.
Now, you might be wondering just how dangerous is this statistical mirage? Well, to understand the extreme danger here, we have to look all the way back to 1926. The statistician G.O. Ewell coined the term nonsense correlations. He realized super early on that if you aren't careful, even the most sophisticated central banks, forecasters, and analysts can be easily fooled into seeing correlations that simply don't exist just because two completely unrelated data sets happen to be trending over time.
So that brings us to Section 1, the spurious regression problem, or the statistical mirage.
The battle for data truth actually has a fascinating timeline. It literally took a century of econometricians fighting against false signals to build the tools we use today. It started with Ewell's warning in 1926. Then, by 1974, Granger and Newbold formalized this issue in econometrics, proving that non-stationary data produces completely spurious regressions. Fast forward to 1979, Dickey and Fuller gave us the math to test for it, and then in 1987, Ingle and Granger absolutely revolutionized how we handle it with co-integration.
So what exactly is a spurious regression? Well, it happens when your standard forecasting models, which rely on data behaving normally, are fed wandering data. Two completely unrelated things might look highly correlated, giving you off-the-charts statistically significant results. Why? Simply because they're both trending over time. If you ignore this, your model's predictions become dangerously invalid. Your inference completely collapses. It's a disaster.
Right, let's move on to Section 2, defining stationarity. Think of this as identifying our stable suspect.
Let's break this definition down into plain English. A stationary time series is basically one where the fundamental statistical properties, like the mean, the variance, and the autocorrelation, do not change over time. When you have a stationary series, you're dealing with a stable distribution. If a sudden shock hits the system, well, that shock will eventually dissipate, and the series will revert right back to its stable, predictable pattern. And this brilliantly illustrates the stark contrast between safe, stable data and dangerous, wandering data. A stationary process is predictable. Shocks are temporary. A non-stationary process, on the other hand, has a wandering mean and variance. Shocks have permanent effects. It's like a giant puzzle where the pieces keep changing shape. Most importantly, non-stationary data violates the central limit theorem and the law of large numbers, which, as we know, are the very foundations of standard statistical inference.
Actually, scratch that. What we've been discussing so far is just weak stationarity, where only the mean and covariance need to be constant. But if you want to be a true data detective, there's also strict sense stationarity. This is a much tougher rule. It means the unconditional joint probability distribution of a process remains exactly the same, no matter how far you shift it in time. It is perfectly consistent across the whole timeline. Okay, moving on to Section 3, trends and unit roots. This is the modus operandi of non-stationarity.
So, non-stationarity usually operates in one of two ways. The first is a unit root, also known as being difference stationary. The simple intuition here is that today's value is just yesterday's value plus some random error or noise. Because of this, the data is just going to wander aimlessly. There's no constant mean to return to, which is exactly why a shock to the system has a permanent effect on the trajectory of the series.
The second way non-stationarity operates is through a deterministic trend. A trend stationary process fluctuates around a specific trend, like a linearly growing line, and reverts to that trend in the long run. The crucial takeaway here is that these two types of non-stationarity require entirely different methods to correct. You fix a trend stationary process by literally subtracting the trend. But if it has a unit root, you must use differencing to render it stationary. Totally different tools for different jobs.
That brings us to Section 4, testing the data. It's time for the interrogation. The first step in our interrogation is often visual. Using the Box-Jenkins approach, we can inspect a correlogram, which maps out the autocorrelation function, or ACF. What you're really looking for here is speed. If the estimated autocorrelations die out quickly, dropping off fast, your series is likely stationary. But if those autocorrelations show a very slow decay, yeah, you've got a prime suspect for non-stationarity.
Now, what's really interesting about this is a brilliant statistical quirk and how we formally test for it. Because it's tricky, econometricians use two tests with exact opposite assumptions. The augmented Dickey-Fuller, or ADF test, assumes the series contains a unit root, so you want to reject the null to prove stationarity. But the KPSS test flips this entirely. Its null hypothesis is that the series is stationary. By using both, you get the whole shebang, a much clearer picture of your data's true nature.
And finally, Section 5, how to stationarize data. Case closed.
We can actually boil all of this down to a highly practical three-step methodology to cure your data. Step 1, you do a visual inspection via the ACF to look for that slow decay. Step 2, you conduct a formal interrogation using the ADF and KPSS tests. Step 3, once you know what kind of non-stationarity you're dealing with, you transform the data either by removing a deterministic trend or by taking differences to eliminate a unit root. To put that into perspective, let's look at a classic example from Luca Pohl's 2007 work on West German disposable income from 1960 to 1982. Looking at the raw data, it has a continuously increasing trend, so the mean is wandering. Plus, the variance increases over time. To fix this, econometricians take the natural logarithm to compress and stabilize that growing variance, and then they take the first differences, looking at the change from one period to the next, to stabilize the mean. Boom! Suddenly, your dangerous data becomes a safe, stationary series. But wait, there is a massive catch here. While differencing 6's stationarity, it deletes highly valuable, long-run information. And this is exactly why Engel and Granger's 1987 discovery of co-integration was such a real game changer. They proved that while individual series might wander aimlessly and be non-stationary, specific linear combinations of them can actually be stationary together. This allows researchers to retain the long-run equilibrium relationships between variables without falling into the spurious regression trap. And for those of you dealing with complex signal processing or higher-order non-stationarities, there's an advanced technique called the surrogate method. Here, you apply a Fourier transform to the original series. You keep the magnitude spectrum to maintain the global power distribution, but you randomize the phase spectrum. Think of it like scrambling the timeline of the data while keeping its overall energy exactly the same. When you apply the inverse Fourier transform, you generate a strictly stationary surrogate time series that preserves the original data's statistical properties but completely strips away the temporal structures causing the non-stationarity. Pretty cool, right? Which leaves us with a final, vital question to ask ourselves. Are your statistical models predicting reality, or are they just chasing a mathematical mirage? As we've seen today, skipping the critical step of ensuring your data is stationary can lead to spectacular forecasting failures. Mastering stationarity isn't just some academic exercise. It's absolutely crucial.
It is the only way to separate the true signal from the noise. Thank you so much for joining me on this explainer, and keep questioning your data.